Hi Charlize, this is the week 4 homework. I'm just going to go through it. For number 1, it's a similar thing as we've done before. It's the checklist. It's kind of having a mental checklist of what to look for when you have a domain. So in that checklist, you check for denominators, radicals, and logs. I think in your class they don't really focus on logs, so I'm mainly going to look at denominators and radicals. In this case, there's both. I identify a square root of x and an x minus 3 as a denominator. Um, for a square root, I can never have a negative number. If I have a square root of a negative number, um, use the imaginary number. So that means x x has to be greater than or equal to 0. For the denominator, I know it can be a negative number, but it cannot equal to 0 because it would give me an undefined slope. So these are the two things we have to check for. This one is easy because x is already by itself. If it were x minus 3, then you would just solve it without the radical. You do x minus 3 is greater than or equal to 0. Is greater than or equal to 3. And that's basically how you would do that. But it's solving for what's inside of the radical. You don't need to include the radical. In the same case, you don't have to include the fraction. All you have to do is set the bottom equal to 0, or in this case, not 0. So x cannot be 3. So I have my two domains. I'm just gonna graph it. So I have 3, 0, and 3. So in this case, x cannot be any number less than 0. So I can do close circle and go this way. However, even though this is right for square root of x, I have to consider that x cannot equal 3. So in this case, you would do this. You would do a hole at 3 and then an arrow. Let's say my domain, hypothetically speaking, let's say my domain was, for example, or actually, we technically, for this domain, x can be anything except for 3. But because we are adding these two different domains together, if one does not work, it cannot be in the domain. For example, -1, even though that can be a denominator, it cannot be in the radical, and so therefore the domain still would not work. And so to write in interval form, I would just do a bracket, comma 3, parentheses, union 3, infinity, and that's it for this question. It's pretty much looking for radicals and denominators, like I said here. And by the way, everything here, you never have to include the radical sign or the fact that it is part of a fraction when you're solving for it. You can just take the part that's inside. For number 2, evaluate the change in the function value f of 3 plus h minus f of 3 when x changes from 3 to 8, 3 plus h. This might seem a little confusing because it's asking from 3 to 3 plus h, but it's pretty simple because they pretty much gave you the equation or like the question that you're solving. You're doing f of 3 plus h minus f of 3. So it makes sense because the word change tells us that we're subtracting. And if we're going from 3 to 3 plus h, we are subtracting this from this. So to do this, typically the structure is f of x equals a function. X is just something that you plug into the space. It's function of x. So in the same way we can say f of x equals 2x squared plus 5x. We can also say function of 3 plus h because it's a function of 3 plus h. So f of 3 plus h is equal to 2 parentheses. And it's very important to use parentheses for these kinds of problems because it is to stay organized. 3 plus h. And you have a choice. You can do them separately and combine them after, or you can just write a super long equation. But I like to keep them separate just so I don't get messed up because I do know that there's a negative here. So f of 3 is a function of 3. So you're plugging 3 as the x. So anytime you see f of something, you're just plugging what's inside into x, what usually is x. To evaluate this, I would FOIL this out. So I would get 9 plus 6h plus h squared times 2 plus 15 plus 5h. I'm going to distribute this here, so I get 18 plus 12h plus 2h squared plus 15 plus 5h. So combining like terms, I see the 18 and the 15, but I'm going to write it as with the highest degree first. So 2h squared plus 17h plus 15 plus 18, which is 33. So that's what I got for this one. F of 3 is easy because it's just numbers. So it's 9 times 2 is 18 plus 15. I just get 33. And it makes sense that we got 33 for both because 3 plus h should just be h more than f of 3. Or whatever the function is. H. Function of h more. So this is my final answer for this one. This is my final answer for that one. And now all we have to do is solve for f of 3 plus h minus f of 3. So I transfer my equation. 2h squared plus 17h plus 33, and I have to remember it's a minus f of 3, so minus 33. So my answer should just be 2h squared plus 17h, and that is the difference, or the change. For this question, it's giving f of x, so it's a function of x, because x is what's plugged into it. I could easily say f of r, it's r squared plus r, anything like that. It's the same thing. For g of x, it's a function of x. G is just a different way to denote a type of function because oftentimes you're not just going to deal with the f of x. You can have g of x, you can have h of x, a of x. There's so many. But it's just another way to say a function. But it's the same exact properties. So basically, it's asking us to find the following or evaluate the following. For this one, it looks confusing because there's a g of 2 inside, but it's still the same. This could very much be f of x. It could be f of 2, but in this case, it's just g of 2. So in this case, what it's telling me to do is I have x plus x f of x, and instead of x, I need to evaluate g when g of x equals g of x when x equals 2. So I'm gonna write it out the long way first, and then we can solve it two ways. So basically, f of g of 2 is equal to, and this is the longer way, but you do square root of 2 plus 1, because I plugged in 2 as x, squared plus square root of 2 plus 1. This is the long way. The shorter way, and this is just because I always prefer to break things up, is you start from the inside and go out. So I am going to evaluate g of 2 first. G of 2 is just x plus 1 when x equals 2. So then I get 2 plus 1. So my answer is square root of 3. Now I will evaluate f of square root of 3 because g of 2 is equivalent to f square root of 3, just like how it's equivalent to this, the middle part. So f of x is x squared plus x, but in this case we're doing a function of square root of 3. So square root of 3 squared plus square root of 3. And all I get is 3 plus root 3. And I will prove to you that it's the same thing here. I basically got square root of 3 squared plus square root of 3. So 3 plus square root of 3. So it's the same thing. It depends how you want to do it. And because we can do f of g of 2, we can also do g of f of 2. G of f of 2 is the same thing. I could write it out the long way and the short way. It just depends what kind you want to solve, if you want to solve one really long equation or two smaller equations. And I always prefer to solve the shorter ones. I'm going to say that g of f of 2 just means that I'm taking g of x and I'm plugging in f of x when x equals to 2. So what that looks like is g of f of 2 is equal to square root, and instead of x, I'm just going to plug in x squared plus x when x equals 2. So 2 squared, I'm always going to be writing parentheses, plus 2. This is my x, my f of x, and I have that plus 1. The shorter way is this way. So I'm always going to be working from the inside out. If you work from the outside in, it'll be more like this long way. Or it would turn out to be more confusing. But f of 2 is just function of 2. So f of x when x is equal to 2. So I do 2 squared plus 2 equals 6. Now, because I know f of 2 is equal to 6, and I can just plug in g of f of 2 into 6. Into g of x. So g of 6 is equal to square root of 6 plus 1. So I get square root of 7. I'm going to prove to you that it's the same thing here. So I get 2 squared is 4, plus 2 is 6, plus 1 equals 7. So square root of 7 is my answer. And it's the same thing. So there's two ways of doing this. And yeah. This one might look confusing, but even though it looks super confusing, when you say it out loud, it's the same thing as what we've been doing. And actually, it's easier because you don't actually solve for an answer. So, FOG. This means function of g of x. Okay? Whatever is first, it's basically like writing this. This is the same thing. So function of g of x. So what this means is I'm working from the outside in again. I'm identifying what my f function is. My f function is f is equal to I'm just going to say f of x is equal to x squared plus x. But this is not asking for f of x. It's actually asking for f of g of x. And it's the same thing, f of g of x. And you just erase the f. So it's f-o-g, if that makes sense. So always reading it out loud helps. I know it still helps me. But f of g of x, since f of x is x squared plus x and g of x is square root of x plus 1, I can just do square root of x plus 1 squared plus square root of x plus 1. To simplify, I would just do x plus 1 plus square root of x plus 1. And this is perfectly fine. In the same way that f of g of x is working from the outside in, so it's a function of g of x, this one is saying a g function of f, basically saying this. And this might look familiar because it's the same thing as this and this, except this is a better way of writing it, because it's saying g of f of x, and you just erase the f, and then you get g of f of x. So basically, you're identifying the g function, which is square root of x plus 1. And then you're identifying what to plug into it. You plug in f of x. F of x is x squared plus x, so g of f of x is equal to square root of x squared plus x plus 1. There is no way to simplify this. You could possibly try x plus 1 squared, but that does not FOIL out to be x squared plus x plus 1, so this is perfectly fine. Okay, so those are how to do those. You just have to kind of remember, if you ever get stuck and don't know what this means, you just think g of f. So in the same way you say g of 2 or f of 2, you can say f of g and g of f. It's the same thing. Okay. So number 4 is related to the questions above. It's the same idea where you have to identify two functions. So typically the rule of thumb is if there is kind of a radical or a square of some sort to any degree, like x3, or they have like this, or even just a normal denominator, it's typically the outer function. So in this case, I know that this has to be plugged into a different function because it doesn't really work. You could honestly, if you wanted to, break it up to be like f of x squared plus 6x, or it'd be like x minus 3, and then the second function would be fx
5x squared plus 6x, and then you plug that into x. But this is the most traditional way. But I'm trying to show you that there's many ways to identify an inner function. Because what an inner function means is that you're plugging a function into another function. So what the question is asking you, what did you plug in to into the outer function to get this whole function? The easiest way to do this is just think f of x is equal to square root of x. G of x is equal to 5x squared plus 6x minus 3. To check your work, you can just do f of g of x or f of g of x is equal to square root, and then I'm plugging, so I already did the square root, and I'm instead of x, I'm plugging in g of x. So 5x squared plus 6x minus 3. And that does match, so it works. Okay, for number 5, these are called piecewise functions. And piecewise functions, they take advantage of the domains. They set very specific domains. So a piecewise function could literally look like this. It could look like just one piece of a different function. It could look like that, and then like that. They could honestly be graphed any way. I could graph any random 5 lines and call it that a piecewise function. But you have to set specific domains. The hard part about piecewise functions is in order to graph them, you need to be able to visualize each parent function. And by parent function, I mean like x squared, the linear, the radical, x to the third, and there are other ones, but they're not really that important right now. But that's the most difficult part, or at least what most people find the most difficult. But for this one, you don't have to graph it. It's just asking you to evaluate these f of. So these piecewise functions, even though it's many little different functions, these are called pieces, and all of these pieces only make up one function. So when you're asked to evaluate f of 0, f of -4, f of 4, or f of 2, you're plugging it into all these little pieces. But you have to be super careful in identifying which piece you're plugging it into. I'll do a visualization of the graph. It's not necessary, but it definitely helps. So it's saying that negative y is equal to f of x is equal to negative x at x is less than 0. X is less than 0 here, around here. So I'm just going to do an open circle and a line. And then these are all points. This is a rough estimate sketch, so it's not exactly exact. Now it's asking for x squared when, so it's asking f of x equals x squared when x is less than or equal to 0, is less than 2. So I'm just going to graph it in a different color. I'm starting from 0 to 2, and I graph x squared. I know that I'm going to close the circle, and then graph it like this. And the most important thing is to never draw the arrows because you're only given a specific domain. For example, this linear function, I could draw the arrows because the domain was saying it just has to be less than 0, but for the x squared one, you cannot because you're given bounds. And as I'm looking, I noticed that I accidentally did a closed circle, but you do an open circle because 2 is not included. The next one you address is f of x equals 4. This is when basically y equals 4, so it's a horizontal line. And 2 is included, so I would just do here, close, or I would do it in a different color. I'm not closing the hole completely, I'm just closing it a little bit so you know that I did not include it in one of my lines. But this is what the piecewise function kind of looks like, and it always helps to visualize this, but now we can actually do the problems. F of 0 is asking when f of x, or the piecewise function, is 0, when x equals 0 for the piecewise function, what does the function equal? So first step is looking for which piece has 0 included in the domain. I see here that it's 0 and here that it's 0. So I'm going to check. This one is just less than, so it's not included. So I know to look at this one. So f of 0 is equal to 0 squared because I plugged it into x squared equals 0. So f of 0 is 0. And we can check the graph and it does make sense. It's right here. Now f of negative 4. Now f of negative 4 is not a number explicitly, but I know that negative 4 is less than 0. So I know to use this equation for my f of negative 4 because it's again asking in the whole piecewise function, which is just f of x, what is f of negative 4? You just have to pick the piece of that function that has negative 4 in the domain, which is the first one, negative x, because its domain as x is less than 0. So I would do f of negative 4 is equal to negative 4, which is positive 4. So f of negative 4 is positive 4. The next one is looking at 4. I know that 4 is not less than 0. It's not in between 0 and 2, but it is greater than 2. Greater than or equal to 2. So I know to use this final piece as in my piecewise function. And this one's super easy because it's saying that when f of 4 or f of x equals anything greater or equal to 2, f of x is equal to 4. So f of 4 is equal to 4. In the same way, you could do f of 5 is equal to 4. F of 100 is equal to 4. Because 5 and 100 are all greater than or equal to 2. And then the last question, f of 2. F of 2. I noticed that 2 is part of the inequality and is stated explicitly in 2 of my piecewise function domains. So I look at the signs. One of them is equal to 2 and one of them is less than 2. So I know I want the equals to one. So it's saying f of 2 is when 2 is equal to or greater than 2, when x is greater than or equal to 2, it equals to 4. So f of 2 is 4 because it's equal to. And it makes sense because f of 2 is here and f of 2 is here. So yes, but what happens if, let's say it wasn't all that perfect and my piecewise function was continuing, my piecewise function had many pieces, but the pieces didn't all connect. Or like this, actually. In this case, let's say this is 2. If I want f of 2, I would simply say does not exist because none of my domains include 2. So there is no value for f of 2. And that's basically all there is. So it is possible to get D and E does not exist.